All right, so let's begin. So the first thing we want to look at, well, we've already started looking at it. We are just basically completing is indices. So let me bring up that reading. We'll read it together, we'll explain it, we'll make it make sense, and then move right into fractions. Then as I said, at the end, we will go through the questions. All right. Do I have a read up? Indices and exponents basics. Ashandre?
Every number or object, as you have seen, can be expressed as one set of that number or object. For example, 1 is the same as 1 times 1, or 3 can be expressed as 1 times 3, which reads one set of 3. If we want to say multiply a number by 1 a certain number of times, we can express it mathematically using indices.
All right, stop. Do we understand what Ashandre read just now? Xavier, unmute yourself. We are talking. You
Not
understand
really.
what was read?
Not really.
Jamilia? No? All right, what he's saying is that every number conceptually is being multiplied by 1. And as we know, or probably we don't know, let me say, 1 is an identity multiplication. What it means is that if you multiply a number by 1, it is still just the number, right?
Yeah.
So 1 times any number at all is still just that number itself. So if you multiply 1 by 1 million, it is just 1 million, right? So conceptually, every number is being multiplied by 1. And we know that this multiplication by 1 doesn't change the number. True or false?
True.
True.
Emilia?
True.
Cool? So that's all it is saying. Every number is basically multiplied by 1. And when you multiply a number by 1, we're just getting back the number. So 1 times 3 is saying, for example, 1 set of 3, which we know 1 set of 3 is just equal to 3. But we want to understand conceptually that every number is multiplied by 1. And then the last part says if we want to multiply, if we want to say multiply a number by 1, a certain number of times we can express it using indices. And the example is here. When we get to it, we'll talk about it. Continue, Ashandre. Indices is?
Oh, facts. Indices is repeated multiplication. The number we want to multiply be called the base number, and the amount of time we want to multiply it by 1 is the exponent, which is represented with a superscript number. For example, 5 to the third power equals 1 times 5 times 5 times 5. This reads multiply 5 by 1 and itself 3 times. The exponent can be...
All right. So what we are saying is that 5 to the third power is just saying 1 times 5 times 5 times 5. Remember we said in the initial stage that every number is being multiplied by 1. So 5 to the third power is just saying 1 times 5 to the third power, which is 1 times 5 times 5 times 5, as is here. All right?
Question, why do you have to
1
multiply by 1?
All right. As we explore indices, you're going to understand how it connects. But what we are trying to say is that conceptually, though we are not often told about it, people always say, in our general math classes, our teachers always say, there is an invisible one, don't it? Don't?
Yeah.
So you see x squared, and teacher say, Before the X, there is a 1, but nobody really mentions it down. Everybody says it's invisible. So we are just making it visible that before every number, there is a multiplication by 1. And as I said, the multiplication by 1 is what we call a multiplicative identity. So each number has this multiplicative identity. Multiply it by 1, you get itself. Cool?
Cool.
Cool. So this is the example. Write in your books 5 to the 3rd power, and let us mention that 5 is what we call the base, and the 3, the subscript number, is what we call power or exponent. So the 5 is what we call the base, and the 3 is what we call power or exponent. Superscript at the top, small and at the top. We have that?
Yeah.
And let us also write what 5 to the 3rd power means. So write it. It means 1 times 5 times 5 times 5. And this reads multiply 5 by 1 and itself 3 times.
Question.
Yes.
What you said the 5 was again?
The base.
Base.
Yeah.
And the 3 is what?
Power
of
or
exponent.
exponent. Right, let us write 5 to the 3rd is equal to 1 times 5 times 5 times 5. This reads multiply 5 by 1 and itself 3 times. We have that?
Yeah.
Yes.
All right, and we also want to understand, you can make a note if you want, that the power tells us how many times we are multiplying the base. So the power is what tells us the amount of times we want to multiply the base. And of course, we know we are always multiplying by 1.
Yeah.
We have that?
Yes, we have that.
All right, you can also put that indices is just a shortened way of representing repeated multiplication. As with the notes that we took earlier on the whiteboard, we would have seen that, as we said, something about that, something. There.
Why Mama calling me? Yes, Mommy.
All right, do I have that?
Yeah.
Free to move on?
Mm-hmm.
All right, let me go back to the whiteboard. All right. We want to establish a few things. As we said, indices is basically repeated multiplication. It's just a nice way to represent repeated multiplication, all right?
Yeah.
So as I said, if we have, for example, a raised to the 10th power, this little arrow here, it means raised, all right?
Mm-hmm.
So, but you just put your little superscript like you know you're doing. For example, if we have a raised to the 10th power, what it is saying to us is 1 times a
times a.
How many times?
A. 10 times.
10 times. All right, Amelia? Davy, cool?
Yeah.
That's what it is saying. All right, so you can go ahead and list them out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now there's also something that I'd like to mention, and you can help me out. If I have, for example, a to the second power.
That'll be
Equal.
1 times equal 1 times A times A.
All right. Hold on. We're not finished. Hold on. Let me just put the next part and then. All right. If I have, for example, A to the second power times A to the second power, this is saying
1 times
A times A.
1 times A
times A
times
1
times 1
times A times A.
times A times
Yeah.
A. All right?
Yeah.
Now, my question to you, what do you recognize with the indices version? All right, hold on, before me ask you that. 1 times A times A times 1 times A times A is the same thing as what?
A to the second power times A to the second power.
Yes, it is also what else? It is something else. Think about it.
Identical.
It is identical, but I mean in terms of an indices expression, it is also what?
A to the fourth power.
A to the fourth power. Thank you. Everybody seen that? It's also A to the fourth power. Are we all seeing that?
Why we couldn't have 1 times A times A times A times A?
All right. We just did 1 times. Remember, the 1 doesn't change the indices expression. The reason why we put the 1 twice is because it is 2 different ones, if you see what we mean.
Okay.
So we have 1A to the second power, which is 1 times A times A, and then this is 1A again. So we just put it back. No big deal, really. As long as you understand the concept that everything is being multiplied by 1. Cool?
Yeah.
So it's just because we have 2A to the second power, why we just do it twice. But no big deal, really. All right, what do you now recognize with this? A to the second power times A to the second power and A to the fourth power. What do you recognize?
A to the second power like the same. Times A to the second is like the simple form in a way.
Is it like?
Simple form in a way.
All right, it is a simple form, but what would we have done to move from A to the second power times A to the second power to A to the fourth power?
Times them.
Anybody see? All right, let me put a next one. Let me put a next one. 3 to the third power times 3 to the third power is saying to us 1 times 3 times 3 times 3, right?
Times 1. Times 1.
Okay, continue. Good. That times 1 times 3. Yes.
Times 3. Times 3.
All right. What is the indices version for this?
You
have the 1 times 3 times 3 times 3 times 1 times 3 times 3.
3
equals 3 raised to the 6.
Everybody see
No.
3 raised to the
2.
3 raised to
4. Hold on. Yeah, 6.
3 raised to the, what's the answer? 4 or 6?
6.
6.
Everybody seen that?
Yeah.
All right. So my question now, A to the 2. Let me all write it different. I'm not good with the writing. Just see with me. I soon learn. A to the second times A to the second, which says equal to A to the 4. Times 1, of course. Always times 1. And 3 to the third. Just see with me, guys. I soon learn. Times 3 to the third is equal to 3. Whoa.
The 2 base them are the same, so it does times the power or
Did
add the
we
power?
really times the power? 3 times 3, 6?
Add.
Add the powers. Everybody seen that?
Yeah.
Seen that, Davy? Damilia?
Yes,
Right?
yes, yes.
And so this is a generalization. This is true for all. Once the bases are the same, when we are multiplying, we can add the powers. Is that cool?
Yes.
Everybody seen that? So go ahead,
Yeah.
take examples and make that notation. When multiplying, once the bases are the same, remember we said just to make it simpler. When multiplying, once the bases are the same, go ahead and add the powers, no problem. Make your life nice and simple. Remember, always multiplying by 1. So put the example when multiplying, and the where's my thing freezing? Everybody good with that?
Yeah.
So we can move on.
If the bases are different, you still can multiply them?
Yeah.
If the bases are different, we can multiply them. But can we add the powers?
No.
No. So the adding of powers is only applicable when the bases are the same. All right? Let me do an example then when the bases are not the same. So that we can see that. Like, can I clear the screen?
Yeah, you can.
Jamila, can clear?
Yes, you can.
Davy?
Yes, you can.
All right. Using a numerical example, of course, because as we already established, just write this and then A times B let me just use that just to show you. Remember we said this is A squared times B squared. Remember, as we can clearly see, are they the same?
No.
A squared times B squared, are they the same?
No.
No.
No, they're not the
What is
same.
A squared equal to?
1 times A times A.
Ah, good. 1 times A times A. And what is B squared equal to?
1 times B times B.
So it's 1 times B times B. And all we'll really be doing is expressing it differently, but there's really no multiplication taking place. True or false?
True.
True. However, as we said before, if we have numbers, so let me do a number one now. If I have, for example, 2 times, and I'm going to put my base, to the second power, and to the second power, are they the same?
No.
Well, not the same base, but are they identical in that sense, in an identical sense?
Yes, they're identical.
Why are they identical? Who answered me? Ashanti?
No.
David also they're identical?
Yeah, because they're numbers.
Because they're numbers. Excellent, excellent, excellent. But we can't add the powers, and we know this. Right, Jamelia?
Yes.
Because the bases are not the same, we cannot add the powers. But we know that 2 to the second power is?
1 times 1, 2 times 2.
Excellent. And 3 to the second power is?
1 times 3 times 3.
Good. So from here, we clearly know what the answer is, but we can't add the powers to find out. All right?
Yeah.
Because the bases are different. And of course, you know they can ask us to give our answer in an indices form, which is base and power, as we said earlier. Or they can ask to give the answer working out the indices. Working out these indices would be 2 times 2. Well, 1 times 2 times 2 times 1 times 3 times 3, which when you multiply it, you really just get I'm waiting on you to tell me the answer.
6 to the 4th. I don't know.
1 times 2 is?
2.
2.
2 times 2?
4.
4.
4 times 1?
4.
4 times 3?
12.
And 12 times 3?
36.
36. So that's what I mean. They can ask us to give the answer in indexed form or to actually work out what is the index. So working it out, the answer will be 36. That makes sense to you?
Yeah.
Even one that we did earlier, 3 raised to the 3rd power, which is 3 times 3 times 3. Times 3 raised to the 3rd power, which is the same thing, times 1, of course.
So the answer would never power of exponent.
Repeat.
The answer would never power of exponent.
And what we're saying to you is that they can ask you to give the answer in that form, where you have base and power.
Oh, okay.
Or you can actually expand and give the answer, depending on what the question asks you. But what you need to know is what a number raised to a power means. And which we already established that it means the amount of times we are multiplying the base. Anybody want to help me with this question? There's a question on my board, magically. Woo! Miss, why can I multiply numbers that are non-identical, but I can't multiply letters that are not identical? Anybody want to provide some light?
You cannot multiply letters.
Because?
You cannot multiply letters.
Well, we can actually. Because A times A.
But you can multiply 2 non-identical letters.
Yeah, but why? We know we cannot, but why? That's the question. Why?
Because
why
that's
can I multiply?
Rule.
Huh?
Because they're not identical.
See? Come on, we said this, we said this in a previous class. What did we say about numbers? And you all write it down. For sure you write it down. And remember, we were talking about the calculator, why the calculator does go ahead and give you an answer. No?
No.
No? Alright, anyways, so let me answer the question then. We said it in the last class that A times B is just equal to AB, which is expressing the multiplication in a different way. But there is no, remember we said multiplication gives rise to an increase or a decrease, but there is really no increase or decrease happening here. True or false?
True.
True. So we are just expressing differently. However, when it comes on to numbers, we say that numbers are always identical. Because we don't know 2 what, or 2 sets of what, or 3 sets of what, but we know that numbers in the general sense are always identical. And if we, for example, are to multiply, we have 2 sets of 3, same thing as 2 times 3, we know that this is equal to
6.
6. And have we given rise to an increase or a decrease?
Increase.
An increase. All right? So with the letters, we are just expressing differently. But with the numbers, there is actually an increase or decrease, and there's an increase in this case. Question answered?
Yeah.
All right? So we're moving on. As I was saying before, good. As I was saying before, 3 to the 3rd power. Let me put it 3 to the 3rd power times 3. We just did it. I'm just revisiting something. We just did it, and we said this is equal to 3 to the, 3 to the We just did it, people.
That is 3 to the 6.
3 to the 6.
Yeah.
What I'm saying to you is that this is the index form. 3 to the 6 is index form where we have base and power. Cool? Or exponent. Cool?
Yeah. Cool.
Now they can ask you to give it in what do you call it? Standard form?
Yeah.
They can ask you to give it like this.
3 times 3.
So this is expanded form. 3 times 3 times 3 times 3 times 3 times 3. Of course, times 1 is there. This is expanded form. Cool? So this 3 times 6, 3 to the 6 power, sorry, is index form. Write it if you must. 1 times 3 times 3 times 3, 6 times is expanded form. All right? And then now remember, this has a value. The question to us is, what is 3 times 3 times 3 times 3 times 3? 6 times.
3 to the 6.
Yes, but I mean, not in index form, no, in regular form. Regular form that you're used to, standard.
3 times 6. No.
Can you repeat the question?
I'm saying this here, this 36
Yeah.
is our standard form, our regular form that we are used to. Cool? 3 to the 6 is indexed form. And this that we have here is what we call an expanded form. Expanded. Now, if they ask us to do it in this standard form, what would our answer be?
Oh. I got you.
Draw for your calculator if you must. Don't feel bad.
$729.
Ah, excellent. Everybody see what we mean now?
Yeah, 730.
So we can be asked to give the answer in index form, or we can expand and give the actual value. Cool?
Yeah.
David, Amelia?
Yeah.
All right, so we covered this. It's covered. Clearing the board? May I?
Yeah, you can.
All right. We're exploring one more thing on the indices, and then we move on to fractions. This is a raised to the 5th power divided by a to the 3rd power. Anybody knows what this is equal to?
Yeah. A to the 2nd.
A to the?
2nd.
A to the 2nd. Agree, Jamila? Zevi?
Yes, I agree.
All right, let us look at it this way. Remember to see with me with my so-called drawing skills. This is saying A times, let me undo that. A.
But suppose a number was before.
Hold on, wait, we could just complete this and then we'll move on. Cool? So we'll do an example in that sense. Times A times one more A. There's a 1 before. Don't mind me. There's always a 1. Times another A times 1 more A. My stuff keeps freezing. You hearing me?
Yeah, I'm hearing you.
Yeah, I don't know why it's freezing. Yours freezing or is just mine?
Sometimes free.
No, what's happening? Come on. Alright. Times A. So this is representing A to the 5th. Cool?
Yeah.
Agree?
Okay.
Over A times A times A. True?
Yeah, true.
Alright, and we already established, probably we should have put that in the note for the things from the last class, that we can cancel when both numerator and denominator are expressed by. I want you to fill in the blank, you know.
What you said?
We can cancel when both numerator and denominator are expressed by what?
When they're the same.
By?
When they're the same.
Well, yes, they must be the same, but they must be expressed by something else. We can cancel when numerator and denominator are expressed by multiplication. Remember we said this in the last class. Huh?
Yeah.
Did we?
Yes, we did.
So we cannot cancel, for example, we can't cancel A plus A over A. Whoa. Sure. All right, good. Remember who said this? People.
Yeah.
Now we can't cancel out this A with this A because the top is being expressed by what? Addition. But we can make this be expressed by multiplication by saying A plus A is what?
A to the second.
2A. 2A, good. Awesome. It becomes A to the second when we are doing what? Multiplying, good. So this is 2A over A. And because 2A just means 2 times A, we can go ahead and
multiply.
Cancel.
And cancel. Making this answer 2. And notice carefully. If you did go ahead and cancel here, which you cannot do, would you get 2? No. So clearly, cannot go. If we do it 2 different ways and we don't get the same answer, it means that one of the ways are incorrect. Cool? So because our numerator here and our denominator here are both expressed as expressed by multiplication, sorry, we can go ahead and cancel. Everybody see that?
Yeah.
There's a 1 times that's here's a 2. Now have to catch me up, you know. Alright, so this A cancel out this A, true?
True.
This A cancel out this one.
Yeah.
This A cancel out this one.
Yes.
True?
Yes.
And we are only left with
2A.
2A?
A times A.
A, Jamila, say it to man, talk up now. We are left with
A to the second.
A to the second power. Now my question to you, what do you recognize is happening between the here's the form, the division, and the actual answer? What do you recognize is happening?
The two maths that they do, the two of them have the same, get the same, gonna get the same answer.
The two of them have the same base, that is true. And what do you recognize about the powers? The 5, the 3, and the 2. What do you recognize about the powers?
The 3 and the 2, as they work, the first power, that is 5.
Yeah, but remember, this will find after, you know, this will find after. So what is the relation between these two, the 5 and the 3 and the 2?
They're the power of something.
The powers are being subtracted.
The powers are being subtracted. Can we all see that?
Yeah, I can.
So this is always true. When the bases, when divided and the bases are the same, we can subtract the powers. So we don't have to go ahead and do all of this expanding form, because we know that anytime at all that the bases are the same, we can subtract the power. Feel free to make a note of that. When divided and the bases are the same, we can subtract powers. Understand, Davy?
Yeah, I understand.
Understand, Jerry, good?
Yeah, but suppose you have a number before.
Yeah, we're going to that. We're going to that. As soon as they finish writing, we're going to that. Do I need to write it when dividing, or you get it when dividing? And the bases are the same, we subtract the powers. You cool with that?
Yeah.
All right, moving on. So Ashandra is now asking me, let us say, for example, we have, this thing keeps freezing. I don't know what's happening. Let us say, for example, we have 2, let's put a bigger number, 15, A to D. Tell me if this was what you mean, all right, Ashandra? No, not Ashandra, Xavier.
No, it's not me.
Huh?
It's not. It's Asandra.
Ashandra, ask me the question.
Yeah.
Okay, sorry. 5A. That's what you mean?
Yeah, and the A would have like an X power.
An X power, no problem. We can put a power. Let me just put second power for now.
What's wrong, class? What's wrong? All the time?
Repeat. Let me. That's what you mean, Ashandra?
Yeah.
All right. Let me just set it out for setting out sake so you can see the light before we explore. This means 15 times A to the third power means what?
1 times 15, A times 15, A times 15, A.
No. Anybody can tell me what 15 A to the third power means?
15 times A times 1 times A times A times A.
Who talking, man? Who talking?
Oh, yeah.
So what is 15 raised to the third power? 15 or A?
A.
A. Good. So this is saying 15 times 1 times
A.
A
Times A times A.
Struggles. 15 times 1 times A times, who master this guy soon. Have some faith in me. Times A. Cool? And then on the bottom we have 5 times
1 times A times A.
and we're just doing the times 1 to emphasize what we're saying, that every number is multiplied by 1. Just emphasizing. I don't think it early, you know? To be carried for. Times A times A. You good with this?
Yeah, I'm good, yeah.
All right.
It's supposed to be 2A.
Yeah, you have 3 A's.
Oh, see there? Thank you. We need to do one with 3 and 3. Anyways, let's go. Remember, we have that 15 and 5 are identical. True or false?
True.
True. The question is being asked to you and me. Remember, conceptually, how many of my divisor, the same divisor, can I get from my dividend? Or what can I multiply my divisor by to get my dividend? True or false?
True.
True. So what do I multiply this 5 by to get 15?
3.
We agree?
Yes.
3. So see there, that is done for us. And then we know that if the bases are the same, we can go ahead and
cancel. So it will be 3A.
wait, so let's give you my answer and I'm finishing my statement.
3A, that's the
3A.
answer.
Any disagreements, any questions?
No.
Say yes to that light now, Ashandre?
Yeah.
So in an event that you get a number, you go ahead and divide your numbers and then apply what you know about the powers and the bases. And of course, just like multiplication, we can have different bases. What happens when the bases are different? Can we still subtract powers?
No.
No. No. Can I clear?
You can.
All right, I'm just doing one more thing, then we move on to fraction. Just one more thing I want to do. Let us say in an instance where I have a to the third power divided by a to the fifth power. What is my answer?
Repeat.
If I have a to the third power divided by a to the fifth power,
A
what
to the
is my
negative
answer?
2. A to negative 2.
A to negative 2. Are we all agreeing?
Yeah, 8.
Lamila? You see how we get that?
Suppose your 5 was negative.
Suppose the 5 was negative.
That's hard.
All right, hear what? This class is not an integers class.
All right, quite.
All right? So we don't want to get into too much integers.
But you would add, and the answer will be 8.
Ah, that's true. But we don't want to get into too much integers, all right? So when we get into integers, then you'll see that light. And you won't think it is hard, Ashandre. Or whoever said it is hard. You won't think so. Cool?
Okay.
And I'm just doing this for your sake. A to the third power means OMG. Means 1 times A times A times A. True? And then down the bottom it means A. Always 1 times, always. Time running from us today, oh God. We're going through the worksheet. Don't mind my body writing. It's 5, right?
Yeah.
How would this look in the expanded form? What would be at the top and what would be down the bottom?
3A.
3A?
I think.
No, listen, what I mean. Remember, when we have expressed both numerator and denominator by multiplication, we can cancel, right?
Repeat that.
When we have expressed both our numerator and denominator by multiplication, we can go ahead and cancel.
Yes, we can.
True. So we have canceled. Oh, I had an extra one down here. You never see 1, 2, 3. Okay. We have canceled. Right? A into A and A into A and A into A. What is left at the top?
1.
1. What is left on the bottom?
A.
Just
1
A?
No,
A.
2. No, it's
1 A to the second.
It is A to the
Second.
So notice, are these the same thing?
No.
Are they the same thing? We just talk about it, you know. If I work a question,
Yes.
They are the same thing. So a to the negative 2 really just means 1 over a to the second power. That's what it really means. We're not going to do more indices for today. We just did that too. You know, little perspective. So we can move on to fractions. Clear and move on?
Yeah, we can.
All right, fractions. Let me see the hands of those who are excited about fractions. No? Nobody? Uh-oh. Gonna be a struggle. No, it won't. All right, who wants to tell me what fractions are?
Fractions, numbers over numbers.
Numbers over numbers? That's true?
Numbers that can go
numbers
into
over
numbers.
Anybody else?
Number that can go.
Oh, Dave is excited. Woo! What else?
Number that can go into a number, a specific time.
Number that can go into a number. Don't write it, don't write. Number that can go.
A figure that have a numerator and a denominator.
Yeah.
A certain amount of times.
Yeah.
And this is the same thing as saying a number. Oh, figure, you said a figure that has numerator over denominator. Anything else, Jamila? You want to share anything? What is a fraction? No?
Part of something.
It's a part of something. All right. These definitions are
somewhat wrong.
Somewhat getting there, but they are not quite there. A fraction, and you can feel free to write my own. A fraction is equal parts of total equal parts of a whole. A fraction is equal parts of total equal parts of a whole. We're getting into fraction today. It's going to be exciting. It's even addition. I probably will just cover the grounds and next class to go into addition. As soon as you finish writing, we'll just do a diagram to show what I mean. A fraction is equal parts of total equal parts of a whole. You have that?
Yes.
All right, so what it means then, for example, we have, no, I want something clear. We have, for example, this rectangle. This is a whole, right? Right? Right here. When we cut this rectangle, whoa. What we are expressing is a fraction. Let me shade one.
Yeah, 1 over 4.
So I've shaded one. And this is saying to us 1
over 4.
1 over
4.
4. So it is equal parts of total equal parts. So we can see that these 4, which is our denominator, they're all equal. And the fraction is the one that is shaded. It is also equal to the other 3. So let me just provide another example, just to explain something. Can this be expressed as a fraction?
1/3.
Yes.
Who say yes?
Me.
Who is me?
Sanjay.
Alright, why? Why you say yes?
Because you split it so you can get, in all, you can get 3 pieces out of it.
So you are saying that this is split in 3 pieces?
Yeah.
And so you're saying that if I went ahead and did this, shade my piece here, so, whoa. Then
You
this
have 1
is
over 3.
1 over 3?
Yeah.
Everybody agrees with that?
Yeah.
David?
Yeah, I do.
Emilia? Let me go ahead and tell you that this is, remember we just said
parts
must be
equal.
equal. Are these parts equal?
No, they are not.
No, they are not. So in order for us to be able to, yes, it cut up for true, it is cut up. All right, so it is being shared. But can we express that a fraction? No, because each of these 3's are not the same. They are not the same. But this cannot be 1 out of 3 because it's not the same 3's. True? So because these are the same 4, we could say that this is 1 out of 4 of the same thing. But this is not 1 out of 3 of the same thing. All right? So the fraction is saying an equal part out of total equal parts. The total parts here are not equal. Is that clear? So this is a fraction. A fraction is equal parts of total equal part of a whole. All right? So I can clear? All right, we also want to put another note in. And we'll explore as we get into fractions. In fraction, conceptually, dividing fractions is multiplying. And multiplying fractions is dividing conceptually. And as I said, as we get into the fraction some more, you'll understand what I mean by this. As soon as we start adding, by the way, you'll understand. So in fraction, conceptually, dividing fractions is just multiplying, basically. And multiplying fractions is dividing. So one is the reverse of the other. As somebody would say inverse. All right, look like we have some time. Can start addition. Can start it. Let us try. Let us try. Let us try. All right. We have 1 over 3. No. Can't be so bad. 1. Sure. plus 1 over 4. We are trying to approach this conceptually. Pay attention. Let us pay attention. All right. 1 over 3 can be expressed in a diagram like this. And if we are to cut it into 3 equal parts, remember the equal parts is important. Three equal parts, and we are of course shading. Is this represented my 1 over 3? Good. And then let me try now to represent my 1 over 4. We're going to talk, I will need to talk. And of course, I have to split this in how many parts?
4.
1 over 4. 4, that's 4?
Yeah.
Just 4? What is that key word that is important?
Equal parts.
Equal. The form of equal. Trying my best. 1. So come down some more. 2. This one go for.
That's not equal.
Who said that? You sure?
Can go on.
Huh?
Can go on.
It can go on, exactly. Thank you, Jamelia. Woman poet can go on. Alright, and this is representing my, oh, don't want to go outside. And this is representing my 1 over 4. True or false?
True.
Alright. Listen to what I'm saying now. Remember, we just wrote that fractions is equal part of total equal parts of a whole. I remember we already established that in order for us to add, then there must be the I word there, which is?
Repeat.
In order for us to add, the elements must be?
Equal.
Identical.
Identical. Excellent. In order for us to add, the elements must be identical. And fraction is equal part of total equal parts of a whole. Now, my question to you, is this 1 over 3 plus 1 over 4 from the same whole? Feel free to think about it.
Repeat.
Is my 1 over 3 and my 1 over 4 from the same whole?
No.
Anybody? That's the way you're thinking. That's the way you think. We're just reasoning. All right, first, are they identical?
Kind of, yeah. Their numbers.
Somebody said, I remember that we can only add things that are identical, and to be identical, things must be of the same type, size, shape, and color. Are they identical?
No.
Hmm?
No.
Don't think about the shapes here. This 1 over 3 plus 1 over 4. Are they identical? Hello? With the men gone?
They are identical.
They are identical. And remember, we said that they must be from the same whole, from one whole rather. equal parts of one whole. So by right, this 1/3 plus 1/4 is from the same whole. The problem we are having, as you can see, is that this is what than this. This over here is what in compared to this?
Less.
Look at the size of this and the size of this. What is happening?
Big.
Huh?
It's bigger.
You see it?
Bigger.
It is bigger.
Larger.
That is the problem we are having. The size of our 1/3 rather is bigger, or 1/3 is bigger than our 1/4. Everybody seeing that?
Mm-hmm.
So our aim before we can add is to ensure that everything is the same size. You following me?
Yeah.
Before we can add, we want to ensure everything is of the same size. All right. Now, as is my representation here, I have them in two different diagrams. And remember we said a part of the same whole. So I am going to put my 1/3 and my 1/4 in one whole. Because they are in one. I just showed the representation differently just now. Let me use a brighter color. So I have my one whole, and I am now going to split my one whole into 1/3 and 1/4. Follow me, follow me. Splitting this into 1/3. Not drawn to scale, but trying as much as possible. Oh, we look accurate. Oh. How we look? Look equal?
Yeah.
Yeah.
All right, so I have split my one whole into 1/3. Everybody see that?
Yeah.
Huh?
Yeah.
Yes.
Mm-hmm.
All right, I'm going ahead now to split into 1/4. The same one whole, using a different color. Help me out, help me out. Whoa, what is that?
Oh.
Trying to be accurate. 1, 2.
Oh, someone.
How we look?
That's not it.
Is it 1/4?
Hmm?
Yeah, the green one wants to go, the last green one go a little bit more.
This one?
Yeah.
Yeah.
Better?
More.
Little bit more.
To the middle.
Yeah.
All right. So are we seeing that the blue lines mark the 1/3 and the green lines mark the 1/4?
Yeah. Yeah.
All right. Let me use a different color. Now remember, guys, our aim over here, so let me all shade just for you to see. Over here is representing.
1 out of the 4.
Is it over here is representing what?
1 out of the 4.
1 out of the 4.
Quarter.
And all of this here, so whoa. This is a different color. All of this. You mean you're thinking freezing? Why am I thinking freezing? All of this is representing our. The purple part is representing what?
The quarter and the third.
Huh?
The quarter and the third.
The purple part? All of this purple part is representing
A quarter.
quarter, and the yellow is representing
1 out of the 3rd.
No.
So Somebody said
the
no.
purple one is the third, and the green and the yellow one is the quarter.
Is the quarter. Are we seeing that?
Yes.
All right, good. Now this is the part where you're going to have to listen to me. Our aim is to split all of, no, our aim is to get the same size. That is what we want. We want to ensure, because this and this are different size, we could go ahead and add them. What we want to ensure is that all of our little partitions are the same size. Is that okay?
Yeah.
All right. So I am going to split my 1/4, that is my 1/3, sorry, that is over here, into equal parts. Using a different color again for the splitting. This color showing splitting. Let me use black. So I'm trying to split into equal parts. This one look equal to the first one?
Yeah.
Like you want to come over just a little bit. Oh, this thing is jumping all over the place. All right, will look better? All right, that look like it. Then we go again. What's happening? I will split again. Do we have equal parts in this our 1/3? Hello?
In our what?
Huh? In our 1/3 here, do we have equal parts?
In 1, 2, 3. From the green.
Yeah.
Mm-hmm.
In that 1/3, do we have equal parts?
Mm-hmm.
Good. We're going to split one of our 1/4 now. Remember
But you put it at the blue line. It should be at the green line.
No man, the green. Let me just recolor the green, because I want you to see that the green is representing 1/3 first. Let me not try to confuse you. Remember that this green line is our 1/3 line, all right? So the whole is split into 1/3, 1/3, 1/4 line rather. Sorry, the green line is our 1/4 line. Remember that, Jamelia?
I'm lost.
The green line here.
Oh,
See that? 1/4, 1/4, and 1/4. Cool. And blue is 1/3, 1/3. So I'm saying from this blue to the end is 1/3. Cool. So I'm saying I have split my 1/3. I just keep this green line. The green line is also a splitting. I just keep it because I want to show you the splitting of the 1/4 in the 1/3. Or you want it color? We can color it, no problem. So we split our 1/4. Alright? Splitting our 1/3 also. Splitting our 1/4. Sorry, we split our 1/3 just now. This one, yeah, go ahead. It's freezing. Splitting our 1/4. Yes, good. Splitting our 1/4 now into equal parts. Miss Lean. All right, we see that?
Okay.
All right, so we split our 1/3 into equal parts, and we split our 1/4 into equal parts. All right? Now remember, it is equal parts of total equal parts. So what it means, everything must be split. We're just trying to understand conceptually. Everything, we have to split everything. So this middle part, we have to split it as well. Cool?
Yeah.
All right, so we're splitting again. Can cover a blue line, just so you're not confused. And we're splitting. This is another 1/4. And over here, we're splitting again. Let us check. Oh. We split our 1/4. And we split this one. Oh, I see what's up. This one not equal. All right, you look better now? All right, let's see how many parts we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh! All right, so we've split our entire whole that consists of 1/4 and 1/3. We've split it into equal parts. Everything look equal to you? Yeah? All right, pay attention now, pay attention. To split something or to cut it up, we are basically performing which operation?
Surgery.
Anybody? To split, to cut up,
Divide.
we are
Dividing.
dividing. Talk up with confidence. We are dividing. Now, what did we divide this 1/3 by? The 1/3 here say no. What did we divide it by? Probably to put the 1/3, 1/4 at the bottom and the 1/3 at the top. Think that we work? Just wait a minute, let me put that together so you can see and then we ask the question. And then the blue line is 1/3. One-third. You see this? Look clearer? Let's confuse it. All right. All right, let's go now. So my question to you, this 1/3 that we have here is divided by what?
4.
Huh?
4.
It's divided by 4?
It's 4 parts.
Xavier, Ashandra, all right, we're listening. It divided by 4. Somebody said divided by 4. Xavier, what do you think? What is it being divided by? The 1/3?
The 4.
All right, Xavier says 4. Ashandra, you gonna leave us?
No.
What is it 1/3 being divided by?
No, I wasn't there.
It wasn't?
No.
All right. The 1/3 is actually being divided by 1/4 and not just 4. Remember, all of this is 4. But this from here to here would be 1 out of the 4. We see that, guys?
Yeah.
So all of this would be 4 for true. But the little ones is really 1 out of 4.
3.
You see that? Talk to me, no man. Are we seeing that?
Yes.
So we have our 1/3. Our 1/3 is cut into 4 equal pieces. So each of them is 1 out of 4. All right?
Yeah.
And similarly, our 1/3 or 1/4, sorry, our 1/4 is being divided by what now?
The
1/3.
1/4. Right here to right here is divided by what?
1/3.
Is 1/3. Good. Everybody seen that?
yes.
1/3. Now here what is what? Not only all right, let us understand this now. That both the 1 and the whole is being divided. Look, so you follow me? Both the 1, which is the part, and the whole is being divided. So if I say my 1/3 is being divided by 1/4, what I am saying is this. 1 divided. Somebody messing with that? By 1/4. And 3 also divided by 1/4. You understand why I said that?
I know, yeah.
Let me just go through it one more time. This, remember that we're dealing with 1/3. Remember that all of this is 1/3, right?
Mm-hmm.
And you see it divided by 1/4?
Mm-hmm.
Now all of, sorry, all 3 of them also divided by 1/4, don't it?
Yes.
Good. Same thing with the 1/4. This 1 out of it is divided by 1/3. And if you notice, all of them are being divided by 1/3, right?
Yes.
So that is why we are saying that both the numerator and denominator are being divided. So this is saying to us 1 divided by 1/4. This is talking all the time. Like we're not going to get to go into the paper. We'll do that first set time in the next session. Plus 1 divided by what? 1 divided by what, guys? 1/3. We just say it, over 4 divided by 1/3. Have I lost anybody?
Not really, no.
Good. And remember we said that in fraction conceptually, dividing fractions is multiplying and multiplying fractions is dividing. True?
Yeah, true.
So 1 divided by 1 over 4 is the same thing like 1 times. Come on, guys. 1 divided by 1 over 4 is the same thing as 1 times all. Anybody to my rescue? It's the same thing as 1 times 4, guys. 1 times 4, which just gives us 4, right?
Yeah.
And 3 divided by 1 over 4 is the same thing as 3 times 4, which is
1. 12.
good. 1 divided by 1 over 3 is the same thing as 1 times 3, which is 1 times 3.
3.
3. Thank you. Anyone go home or leave? And 4 divided by 1 over 3 is the same thing as 4 times 3, which is
12.
12. Good. Now, do we have total equal parts? Total equal parts. Do we have total equal parts? Come on. Yes. And the total equal parts is?
1 over 12.
12. Good. It is 12. So because we now have equal parts, we can go ahead and add. We see that?
Yeah.
Good. And 4 plus 3 is?
7.
7. Making our answer simply that. We went through all of that to say that. Any questions? Feel free to ask at this time. Any questions, guys? So this is just a conceptual approach. Can I clear? I'm gonna see if I can get a new one. Can I clear? Can I clear?
Yes, you can.
All right. So this is conceptual. It is conceptual. Now, procedurally, what you're going to do on the test, because you're not going to have all that time to sit down and draw and all of that. So that is just for you to understand the concept. Procedurally now, we can name this fraction C. We're ending on this note, guys. Don't worry, we're soon gone. We get to go home.
I'm home.
This is here. This is C. And we can name this one song. Oh. So. All right. And procedurally now, all we are doing is multiplying the denominator of saw by C and the denominator of C by saw.
1 over 12.
Repeat.
1 over 12.
The denominator of saw is 4. Can we see that 4?
Yeah.
So we are multiplying C by the denominator of saw, which is 4 over 4. Remember the 4 down here, so mean 4 whole. 4 equal parts, rather, sorry. 1 whole, 4 equal parts. So we're multiplying the denominator of saw by C and the denominator of C by saw. Uh-oh. You understand me, guys? That's all that matters. So 4 times 1 is?
4.
4 times 3 is?
12.
12. 3 times 1 is?
3.
3. And 4 times 3 again is?
12.
12. See, we
How
have,
many say
repeat?
we get 1 over 12?
Yeah, you did, but we just want to understand the procedure. We never say wrong, honey. If you felt that way, I humbly apologize. Alright, so the answer is 7 over 12. True? Hello? Any questions?
Who could I say 4 into 4, 1, 4 into 12, 3, 3 into 3, 1, and 3 into 3, 1. You get 1 over 12.
We could say repeat.
Could I say 4 into 4, that is 1. 4, 9, 12 are 3 times. 3 into itself are 3, and 3 into 3 are 1. You get 1 over 12.
Hold on, I'm going to follow. What are you talking about here? Up here, sir?
No, the last part.
Down here, sir?
Yeah.
We could say what now?
Who could I get? If we could have cancelled out everything, we could have get 1 over 12.
No, if you cancel, remember, cancel must go with top and bottom. So if you cancel, do just go and get back 1/3. And if you cancel here, we just go and get back 1/4, don't it?
You can have to cancel it, top and where you can cross it.
The cross, you mean so?
Yeah.
That is for multiplication.
Oh.
Right?
Yeah.
So we don't do that. Remember, canceling, everything must be expressed by multiplication. If you're going to cancel, everything must be expressed by multiplication. Cool?
I like that a while ago.
Cool?
Yeah.
Yeah.
But it is also important to note that our answers should always be simplified. So in this case, 7 over 12, it cannot be simplified because I don't think you're going to 7 and 12 without leaving a remainder. But if, for example, we had a case where the denominator and the numerator had a common factor, we should go ahead. Everybody know what I mean by simplify?
Yes.
All right, so if it was a case, always simplify the answer, right? Answer should always be simplified. All right, and I know that some of you are probably used to the LCM method for adding fractions. Anybody? Nobody used to the LCM method? Nobody not add fractions before?
Yeah. Lowest common factor.
Yeah, you use the LCM method, right?
Yeah.
Yeah, but sometimes it probably is difficult to find the LCM, but this method here, the seesaw method, is a sure one. Because all you're doing is taking the denominator for this, multiplying it by the first one. Taking the one for this, multiplying by the second one. All right?
Yeah.
Any questions?
No.
So always, answer should always be simplified. Let me put when possible. All right, we have had a whole mouthful for today.
Can I ask a question, miss?
Always.
Can I ask a question?
Yes, please do.
So based on what you have done here, it is correct to say that no matter what fraction I have, all I have to do is multiply the denominator of C by SAW and the denominator of SAW by C, and I will get my answer.
Facts. Always so. Always. Standard.
Okay.
And then somebody might ask me, Miss, what, and I'm just saying this generally, just generally. Somebody might say, Miss, what if I have 3 fractions? What if I am adding 3 fractions? Anybody want to think about what I would do then if I am adding 3 fractions?
The denominator must be the same to get by the same denominator, and then you add the numerators.
Yeah, the denominator must be the same in order to add, but how would we apply the seesaw method? Think about it, think about it. Anybody?
If the C answer is the same and the other one is the same.
What if they are not the same? All of them have different denominators.
Find something that all of them can go into.
That is LCM method. How we apply the seesaw method? So one way is to apply LCM method, yes, find something that all three can go into. What is another way if we're going to use this seesaw method here?
Maybe you can add them.
Add all three?
Yeah.
You think so, Jamila, that we can add all three for the seesaw method? Well, we can, but how? That is my question, because we can, but how? Nobody? All right, probably tired.
Find the LCM.
Huh?
Find the LCM.
Yes, we can find the LCM, but I'm asking, using the seesaw method, how could we add 3 fractions? If we're using the seesaw method. No? Tired?
Yeah.
We could do them 2 by 2. So we could do the first 2 using the seesaw method, and then the answer that we get, we add the next one to it using the method. Is that like there? Eh? No? Next class, you're probably tired.
Everybody tired?
Them look tired and I see them face and who stop shoving like them asleep. Alright. Alright guys, I have held you past your time tonight. Nowhere in my intention. It goes like that sometimes. Alright, so thank you for staying and participating. And we will meet again on Tuesday. Anybody? Oh, is Ashandre must share with me? Or is Xavier never shared the last time? I must share class. Is you Xavier?
I have a friendly reminder to hear.
Me share.
Repeat?
I have a friendly reminder.
Yeah, I heard you, but I'm asking, which one of you, Xavier or Ashandre, didn't share what you learned the last time?
I should share now.
Xavier?
Oh.
Yeah.
Alright, go ahead. Tell me something.
Learn about laws of indices, and we learn that the number is known as the base, and the other number on top of it is known as the power of I don't remember the other word.
The power or, not of, or. Power or.
Or.
What is the word, Ashandre? Power what?
Hmm?
The superscript is known as the power or what? Jamila, can you help me? Power or?
I never did write it up because I never did hear what she said, so I just write power alone.
Power or exponent?
Yeah.
Exponent. E-X-P-O-N-E-N-T. Exponent.
Yeah.
Anybody want to share anything?
What you said?
Anybody else want to share anything that you've learned today?
In a fraction.
Anything at all?
Like,
Anything?
if you have a circle,
Mm.
no matter what you do, it's not gonna be the same.
Ashandre, like you want me to teach some more?
No, you see, like the circle, see you cut up in a 3.
Yeah.
Not gonna be this.
Not gonna be
Oh, if you cut up in 3, it won't be
equal.
equal. And if it is not equal, it cannot be expressed as a fraction. Good. But we could cut it up in, 4 or one of those even numbers.
Cut it in a 2.
And it can cut into 3 equal parts, It can.
No.
Google it. I won't teach anymore. I'm really tired of it. Let's go, Jeremy.
Just to remind everyone that, are you hearing me, everyone?
Yes.
Yeah.
That coming in about another 3 weeks or so, you're going to be starting to use the 40 hours to a grade 1 in CXC math textbook in your class, and everyone will need their own copies to actually be doing the activities when that time comes. All right, so everyone needs to acquire their own copies of the textbook. We'll also be emailing you guys the syllabus so you can keep a scope and sequence, so you guys can keep track of what's going on, what's coming next, blah blah blah, and so you can read ahead, because the syllabus doesn't just have content, it doesn't have just topics, it also have the content, so you can actually read ahead of the teacher. So when it comes to class, it makes everything much faster for you. Finally, if you're enjoying yourself so far, we encourage you guys to share on our Facebook page, may leave a comment, leave a review, so that others can know what you guys are experiencing in the class. That's all I have. All right. Over to you.
What name? Ashanjay?
Yes.
Just take a screenshot, please, because you never send me an email. Try the questions. We never get to go through them this week, but Tuesday, hopefully, we'll try go through them before we start, all right?
Yeah, I'm screenshot it.
You screenshot it?
Yeah.
All right. So, guys, that's it. Thank you again, and we will meet on Tuesday. Have a great weekend and all. Remember, church Sunday.
JV couldn't wait. You can stop recording.
Bye.
All right, bye.
You can stop recording. You can stop recording.
Oh, yes. I forgot.